Hi, my name is Tom and you are at level 28 in Mastering Special Relativity. This is the C level, not for all. We will talk about length contraction, classic and real world. We will derive the mathematics and apply the equations that came out of it. Are you ready? Let's get into it. Let's bring my focus back to the screen. So in the previous two levels, the A and the B level, I introduced this setup. Two trains, 20 meters long, blue train moving at 80% of the speed of light. And this is what happened in the animation. It contracted down to 12 meters. And this is what we call classic time dilation. And this is the math behind it to go from 20 to 12. Then we talked about the real world. What would happen if you would look through a telescope? And then we found out that if the train is moving at you, it's much bigger. And if it's moving away from you, it's much smaller. This is what we saw, 60, 6.6666. While the truth is, it is 12 meters long. So we have two people who agree that they both have a train of 20 meters long. But with the one, the stationary train sees the moving train coming at him at 60 meters, moving away it's 6.666 meters, and Einstein is telling everyone it is 12 meters. And that's exactly the same thing the person in the blue train saw. So they are not agreeing on their observations. And if these were scientists, two things can happen. One, they have a major breakthrough and discover special relativity, or they get into a fight. I hope not. Let's see. Well, at least they will have a headache, in both cases. What is going on here? Let's see if we can make this a little bit more intuitive. We'll start with classic length contraction. My secret special notation. It's extremely important in special relativity to know who's talking about what. Location, time, velocity, what event, which observer, etc. So I always note it like this. So here we have the Lorentz transformation. I introduced a V prime for velocity, which is just the velocity over c, so it's the fraction of the speed of light. We see gamma, the Lorentz factor, and we see the Lorentz transformation in there. So you should be really familiar with these equations and why I'm using all these subscripts. Which event from which perspective? If you would take two events number 1 and 2, and you would subtract the x location through the eyes of observer 2, divided over c, you will see that you get back the same equation, the same Lorentz transformation, but now with the deltas in there. So you can just put deltas, right? So this is what I did for the location. And now imagine the stationary observer is photographing or filming a moving rod. And one end of the rod is event number 1 and the other end of the rod is always event number 2. So when the picture is taken, he will see the rod on his picture, and those events are at the same time from the perspective of observer 1, which is the stationary observer here. Let's also consider another observer who is having the rod in his hand and is moving with the rod. For the observer 2, the rod is not moving. It's always stationary from his perspective. So he's moving along with the rod. And then, let's go one step back. 2 steps back. Sorry about this. The same time, if both events happen at the same time for observer 1, delta t, between the time between the two events through the eyes of observer 1 will be 0. So we can leave out the final piece in the delta equation. So we get that the difference in location through the eyes of observer 2 is the same as the difference between the two events through the eyes of observer 1 multiplied by the Lorentz factor gamma. So this equation simplifies, and it simplifies to this. So we get that the stationary length, the length through the eyes of the observer traveling with the rod, is gamma multiplied by the difference between the two events through the eyes of observer 1, the one that was taking the picture. And because gamma is bigger or greater than 1, the stationary length through the eyes of observer 2 in this case is stationary relative to the rod. Observer 1 is our stationary observer because we are observer 1. I know. I know. It's crazy, this stuff. You have to be so careful who's talking about. Even now I'm making these mistakes all the time. So, but from the perspective of observer 1, the rod is moving. From the perspective of observer 2, the rod is stationary. But the thing is that the length witnessed by observer 1 will be shorter than the length of the rod witnessed by observer 2. In other words, in plain English, moving stuff shrinks. And that's it. That's classic length contraction. Oh, here it is again. So, event tables. And next to the space-time diagram, I'm fond of event tables. So I have put in the things we know. Let's say event number 1 is the middle of the moving train, observer number 2, at 50 seconds on the clock of observer 1. Event number 2 will be the start of the train at 50 seconds on the clock of observer 1. And event number 3 will be the end of the moving train at 50 seconds on the clock of observer 1. You can just put in the things we know. The clock of train 1 will be 50 and for all 3 events, and we will know where the train is. We know that the middle will be where the middle will be. And is this right? Is the start of the train at 50:10 and minus 10? Yeah. I don't think that's right. 50 seconds. No, I don't think this is right. No, it is. You know, these are the events from the perspective of observer 2. And observer 2 will say the middle of my train. If the observer 2 is in the middle of the train, he will always say this is 0. Event number 2 will be the front of my train is always 10 meters in front of me, and the back is always 10 meters behind me. Because, you know, my train is not moving. It is 20 meters no matter what someone else is saying. So 10 minus 10 are good there. 50, 50, 50 is good. And the middle of the train will be 0.8, which is the velocity times 50 seconds, will be 40 away. So x will be 40c, but x over c will be 40. Yeah, I thought I made a mistake here. And now it's just, you know, again, let go of your intuition. I let my intuition interfere. Don't do this. Trust the math. Just punch in the numbers and you can calculate 30, 46, 22, 34, 38. But still, if you plot this in the space-time diagram, it's much more intuitive than taking the words, and it's much more intuitive than using the math. Classic length contraction. Here it is. Let's look at telescope length or real-world length contraction. I'm assuming that you saw real-time time dilation, where I make use of these 45 degrees projection lines which intersect the guidelines of the moving train. The contracted length is just 12, and I can write down the equation for the middle of the train, which is the not dotted line, blue line. This is the projection line along which the light travels from the moving train back to the telescope of the non-moving train. So event number 4 is when light starts to travel from the back of the train all the way back to the telescope at event number 1. Event number 5 is when the light of the front of the train starts to travel back to the telescope, and they both arrive at the same time here, and then you will see a telescope length, a real world contracted length of 6.66666. And we can derive this because we can also write down the equation for the front of the train, which is this one, and I abbreviated contracted length with CL. I also introduced I see x prime, which is x over c, and v prime is v over c, etc. This will be the equation for the line of the back of the train, and now you just have to find the intersection of the yellow projection line with the 2 dotted blue lines, and if you put it all in and you shovel a bit, you will get this. The length through the telescope, which is the difference between the x-coordinate of event number 4 and the x-coordinate of event number 5, will be the contracted length divided by 1 plus v over c, which is in this case 1 plus 0.8. Moving away, same story. Pick a time on the clock of the train, the non-moving train, the red train, the telescope train. Drop down a 45-degree projection line, intersect it with the back and the front of the train moving through space-time. Do the math and you will get an equation where it's not divided by 1 plus v over c, but 1 minus v over c. And here it is, all in one single picture. We talked about this in the B level, but just, if you didn't see that one, you can go to this website. It looks like this. Here are all the events I talked about, and you can switch perspective and see what's going on and why contracted length and real world contraction length is different. You can even change the speed with your mouse. If the trains are not moving, both of them, then everything comes together. If you go to the speed of light, stuff goes into a line. I'm not really sure my equations hold up here. I think they break down because of the singularity. Just go to 0.95, then you should be fine. And you can play with it and understand special relativity way better than looking at the Lorentz transformation or listening to someone like me talking for, I think, about 13 hours from level 1 all the way up to here. Just use the space-time diagram. It's so easy, it's so intuitive, and you can just go to this website and learn all about it. Let's go back to my slides again, which is this one. If you want to know more, pause the video. Here are some references you can look up, and this is it. I want to thank you for watching. If you want to see more, if you are, this is level 28, what about those 27 levels in front of it? Here they are. Pause the video, have a look. These are the first 18, and these are the others which go all the way up to level 34, twin paradox. If you just want to follow the headlines, follow the green. If you want to truly understand special relativity, do the intermediate steps as well. Again, thank you for watching and hope to see you next time.